Hello, hello, hello. Hi. Oh, Velda, I can't be Gorley.
Hello, Veldak.
Veldak. All right.
Hello, J0 Han Anderson.
Oh, Jonah Anderson.
Hello,
And Pegorley. Everyone, hi. Alright, we're going to work on the programming language cast today again. Just like we've been doing. Nice echo. Yeah, how do I get rid of the echo? I mean, I guess I removed... No, I still have like the noise suppression, the noise... I don't know, I guess it's because the microphone is turned a little more towards the speakers compared to the old microphone. Yeah, I don't know. It's not too annoying, is it? Well, I mean, the TTS is not happening all the time anyway, so... Probably fine, right? Greetings, Jerem. Oh, look, my bot is still working. Nice. I feel like when I actually did rewrite my bot into cast, it actually stopped disconnecting from Twitch. I feel like my old bot, which is written in Rust, was stopping receiving messages a lot of the times for some reason. I was using a library there. Maybe the library was not implementing like the ping ponging correctly or whatever. I don't know. Another idea is that my bot is actually crashing. Let's actually check this. Maybe my bot is crashing. And that makes it like restart automatically, but the other one is like trying to do it gracefully and then it fails or something. I don't know. System control. Status Scooby bot. Let's see. Active from 6 hours ago. I think yeah, I think I booted this PC 6 hours ago. Okay, I mean technically it's only 6 hours, so it's not like that long. Usually my bot was breaking like after like a day or something. Anyway, hello guys. So I was working on the thing that I did not finish last time off stream. And I did finish it. So we do have inference variable scopes attached to every inference variable. So every variable knows which scope it comes from. And that fixes the performance a little bit. The thing is though, the performance problem that I was fixing is the performance because I introduced like some new features of the language and like better type system things and stuff. And when I was doing that, the performance became like 1,000 times worse. And now with this thing that I added, the performance is now like, instead of 1,000 times worse, it's only 10 times worse, like 100 times worse, something like that. So it is still worse than it was originally when I was solving my adventive code, but it is, at least we can drop into the REPL like immediately. It looks like I have some debugging enabled currently. But yeah, basically, like parsing the standard library is instant. If we compare this to, let's just check out the let me see what I did here. Something I was like testing something. This Let's change this to trace. Change this to trace. Yep. You have an idea to boost performance. You allow people to make functions, but inside the functions, they can only write assembly. Trust. Okay. Anyway, so like, look this. We go into the standard library. It's not immediately, right? We see a little bit of time. Like, maybe like, let's just you know, let's just do examples. Hello world. How about this? And then we do time it, right? So there we go. This is half a second, right? Half a second. Let's now let's have this beautiful commit message. I guess you're Christmasing in January. Yeah, we don't do Christmas, we do New Year. Here. What was I trying to do? Like, let's just check out the main branch here. And let's now, in the main branch, try to go into the REPL. And as you can see, so as the only thing that I changed is this new thing. Yeah. So like, that's how bad our performance was. It is like something like 30 seconds, and now it's half a second, so 60 times better, or something 100 times better than in the main branch. But at the same time, this is actually going to finish at some point, right? Oh, yeah. There is also like this bug. I did fix that though. That's irrelevant. If we try though to check out the version that I was using to solve the advent of code, let's see, Kuviman advent of code. And what is the version that I'm using here? Let's just say, look at the log file from 2 weeks ago. We need the cast lock revision this. Let's just check out this revision. Git check out this. Ah, shit, what did I do? Did I copy the entire... thing? Alright, so here's our revision. And now I try to go into cast the REPL after I compile it, of course. By the way, the compilation times of a camel, look at this. Did you see that? Like, yeah, my project is pretty big. Even in a camel, my compilation times are not that good anymore. I need to wait for like 5 seconds or something. Sometimes 10 seconds, sometimes even more than that. But yeah, you see how this is even faster, right? If I try to time examples hello world, this is 0.3 seconds, right? Or what should we look at? At the total CPU, 0.45. Pretty stable, right? Switch to Haskell theoretically should be better. The compilation times? No, I know that it's worse. Okay. So yeah. 0.4. Let's go back to the nope, this is main branch. Does this switch back to that one? Yeah. Let's do git check out inference for scope. That's my branch. So in this branch, let's see how long it takes to build it. .2 seconds. Yeah. So once again, time, cast, examples, hello. Okay, so it's not like that much slower, at least like to parse the standard library, right? So we went from 450 milliseconds to 600 milliseconds, right? Yeah, so it's not that bad in terms of like doing the hello world, which includes basically parsing, compiling, like doing everything with the standard library, from 0.4 to 0.6 seconds, which is like okay, right? I think. So in standard library, we have 1,000 lines of cast code. So 1,000 lines takes. Okay, let's just say that 1,000 lines of cast code are being processed in 0.5 seconds, in half a second. 2,000 lines a second. 2,000 lines a second. This project is 17,000 lines. Let's say it's 20,000 lines. And we do 2,000 lines a second. Compiling this from scratch in cast, in theory, with the current version, should take 10 seconds, right? 2,000 lines per second, 20,000 means 10 seconds, which is almost the same as the OCaml, right? OCaml like takes 6 seconds something. I did not even compile from scratch probably, right? So yeah, I think it's not too bad, but if we talk about like the actual runtime, so we go into the advent of code that we were solving, the advent of code, right? And we try to run the day one, right? There we go. Day one on like the actual input, right? So there was what, 4.5 thousand lines in day one or something, is that correct? Yeah, there's like 4.5 thousand lines, and we need to do some stuff here in day one of advent of code. So we run it, we run this, and it takes 1.5 seconds to run the day one of advent of code, part one. If we do this though using this new version, we need to do 4.5 thousand lines here, and I'm still not at the line 100. Most time is taken by outputting to the console? I don't think so. I think that is not true here. Well, I mean, I guess it's like you say, it's because I'm printing. Yeah, it's not. I'm pretty sure it's not. But yeah, this thing is still like a lot slower at the runtime. So why is that? I know exactly why though. Is because once again we're doing the substitutions. I think the problem that I'm having is basically this is definitely slow. Yeah, this is a little slower, right? A little slower. So the problem is that that I'm performing like substitutions of things at runtime. What does it mean by like substitution? So what I'm trying to do here is let's say that I have a generic function, I guess it's about the generics mostly, right? So when I say 2 plus 2, 2 plus 2 is technically just calling the function add using 2 and 2. Add is a generic function which works for all t's. You have a t and b t, and then there is something, you know, this is calling native function or something using a and b. So what's happening at runtime is we're trying to instantiate this while saying that this is an integer or something. Let ChatGPT write a new language, add many agents to iterate on those languages and test them. Let's leave that to somebody else. Maybe. How about I don't do that? Maybe you do that, Valdek. If you want. Did you try solving your advent of codes yet? As you were planning to. So right now I'm actually instantiating the generics at runtime, right? I do instantiate them only once, and then like next time I'm like just basically like every time so I'm doing this at runtime, but what? But we we just see the memoized version of this function, right? So like we just we do it at runtime, but only once, basically instantiating this, right, with an integer, specifically this, right? But what does instantiating this thing even mean? Because I'm still not creating the monomorphized version of this function. I'm still working with the original like compiled version, which still contains t's as variables, which means that at runtime, when I'm actually calling this function to figure out what like this thing actually is, I am at runtime figuring out from my current context what t is and like replace that so that we know that the type of this thing is actually, you know, t and t into t. Right, so we need to replace this with like int, and into int. So this is what's happening every time I call the function. Ideally, what we need to do is like at runtime, all the type information needs to be completely erased. But we don't do that, especially because right now for every value, I'm also storing the type of the value in the current interpreter. I'm not sure if like that's really needed during compile time. I'm using the interpreter during compilation, right? So I think that might actually be needed. But I don't know. We can see if it's actually needed or not. But it takes a lot of time. Also, it basically means that I'm doing the monomorphization, but not exactly monomorphization. I'm doing monomorphization every time instead of just doing it once, which is leading to the performance problems. Obviously. You got depressed, you have only 1 week of no working left. But I thought about it every day. Made a lot of progress in Factorio though, nice. Nice, Factorio. Don't remind me of Factorio, please, thank you. It's too early for now. Sometime later, okay? Remind me about Factorio like in 1 year or yeah, something. I need to not even think about it. All right, so I found this thing. Existentialize your generics. I'm just wondering what this is. I just saw the anti-language developer linking this thing. So I'm wondering what this is about. Because maybe it has to do something with it, because here's the abstract. The two main approaches to compile generic programs are dynamic dispatch and monomorphization, where the latter is typically preferred in the context of load and latency applications, where the overhead of boxing may be prohibitive, It also comes at the cost of the important limitations in terms of modularity, expressiveness, and code size. The Swift programming language proposes an interesting third alternative that addresses these shortcomings, supporting dynamic dispatch without requiring boxing by factoring method tables out of object headers. This paper examines the merits of that strategy, which we call existentialization, across different programming languages. Our study shows that existentialization can produce code with competitive performance with respect to monomorphization. So, like, I guess the core idea here is that instead of doing monomorphization, we are doing dynamic dispatch without boxing, right? By factoring method tables out of object headers, whatever that means. I'm not sure if this is like relevant to my current problem, but it's interesting. Generic programming is the discipline of lifting generic applications from concrete implementations. Naturally, applying this discipline requires one mechanism to express these abstractions, for example, parametric type polymorphism, and another to compile them into non-generic definitions, usually implemented in one of two ways in mainstream programming languages. The first, dynamic dispatch, consists of deferring the selection of the function being applied to runtime. The second, monomorphization, consists of creating a specialized copy. Languages geared towards low latency opt for the latter. The appeal is that monomorphized code can be compiled as efficiently as if it had been written without generics. However, this technique also comes at the cost of three important limitations. Firstly, monomorphization implies that the definition of a polymorphic function may potentially be recompiled at each of its call sites, which severely hinders separate compilation and works against binary compatibility. Secondly, not all functions can be monomorphized. In particular, recursive calls nesting type arguments in structural types must be avoided lest they... What is lest? Thus, they would generate unbounded sets of monomorphized copies. Recursive calls nesting type arguments in structural types. I'm not sure what they mean. Okay, but okay. Lastly, monomorphization may lead to code blow-up, since the same definition might be copied many times in compiled code. Dynamic dispatch does not suffer from any of these limitations, but brings another challenge to the table. If f is compiled only once, then how are its arguments supposed to be represented? The answer is simple in most object-oriented languages, e.g. Java, where all the values are primitive ones, but primitive ones are boxed along with object header, providing the runtime information. That's how, like, basically all of the languages that I have worked with work, I guess, that are garbage collected. The thing, I guess, the camel is the same. With this arrangement, arguments to generic functions can be passed as type-raised pointers to boxed values, relying on object headers to dispatch method calls. Arguments to generic functions can be passed as type-raised pointers to boxed values. Yes. What a stream title. Hello, Codingram. It is a title. Hello. How are you doing? We work on cast today again. I'm reading this paper about generics, the third approach that is not dynamic dispatch and not monomorphization. This is pretty short, actually. Maybe we just read it fully. Yeah, so we just do type erasure, and at runtime we don't have any type information. So like ideally that was my original plan. Let's see what they say here. In systems programming, however, boxing is heavily discouraged, right? So like the problem with boxing is the runtime overhead due to indirections. Instead, one should aim at representing data in contiguous memory regions to support cache-friendly memory access patterns. Further, when large collections of homogeneous data are considered, storing multiple references to the same header is space inefficient and may also hinder optimizations. Well, I mean, actually, like, hold on. What do you mean, like, header? What do you mean, header? What do you mean by header? Maybe OCaml is working in this same way. That they are trying to describe here. One workaround is to box, like, because what is the header there, right? We just basically have like, you know, camel, basically every value is represented like has the same size, which is why basically everything is boxed, but what is behind the box depends on the type. So when you call the function, like when you write code, knew about the type, but then there is no actual header that is being stored, right? Hold on, OCaml object representation. Well, I mean, I guess the header of an object would be the size that is stored on the heap, maybe. I don't know. I don't even know if that is necessary, though. If or if it's just like literally just a pointer. No, maybe there is still a header because the garbage collector still needs to know about these structures, right? Hello, Hisoka. You have something here. Alright, anyway. What do you hate programming? Is OCaml driving you nuts? I don't know. What is the reason? Why would you love programming? What is there to love? Everything sucks. Well, so we need to fix it by creating our own programming language which doesn't suck. Then we will start loving programming again, I guess. Right? Right? One workaround is to box values on demand into existential containers. In Rust, for example, one can use a so-called din trait to define a generic operation that does not require monomorphization. This trick is not without drawbacks, though. On the side of ergonomics, one issue is that existential containers weaken the guarantees of the type system can offer by erasing specificity, opening the door to a well-known issues such as the binary method problem. What's a binary method problem? On the side of performance, the wrapping of a value into existential container might require costly dynamic memory allocation. Even worse yet, the technique scales poorly in cases where parts of a generic data structure must be boxed in rather than the whole. Parts should be boxed. For instance, transforming a vac circle into a vac boxed in shape in Rust may turn a constant time operation into a linear one. Yes. Understandable. The joy of looking back and seeing that we solved the annoying problem feels pretty good. You're pushing through your hatred, proves the girth of your Kuvitelligence. My Kuvitelligence is not enough to like. What does girth mean? It's like birth and girl at the same time. What does it mean? Girth. A band attached to a saddle and fastened around a horse belly to keep the saddle in place. The old V-table is coming back. Well, I mean, the V-table is still used, like in Rust. This boxed in shape. This over here is basically the fat pointer to the data and to the V-table, right? That's how it works in Rust. I'm not sure if like the approach that they are proposing here, the Swift programming language, I guess, is what introduces that, is still a V-table or not. But they propose an interesting solution to alleviate these issues. When a polymorphic function cannot be monomorphized, either because of separate compilation requirements or because monomorphization would not terminate, it is compiled to a monomorphic version accepting its type parameter as additional term parameters. Intuitively, the idea is to factor out the information that would otherwise be stored in object headers so that arguments to generic parameters can be passed as typed arrays pointers to unboxed concrete values. Wait, what? Hold on. I think okay, hold on. I had this idea that we actually don't erase the types fully, but we pass around the types as like the information that we need about the types when compiling. So is that like the same thing? The idea is to factor out the information would otherwise be stored in the object headers so that arguments to generic parameters can be passed. Arguments to generic parameters. What do you mean arguments to generic parameters? It's just the generic parameters are passed at runtime or something, right? As type erased pointers to unboxed concrete values. But what concrete values? This approach, which without existentialization, is an important part of Swift's strategy to uphold resilient binary interfaces. Nonetheless, the compiler systematically favors monomorphization if applicable, suggesting that existentialization should be used sparingly when performance is a concern. This paper challenges that assumption. Specifically, it shows that existential code can run as efficiently as its monomorphized counterpart on state-of-the-art virtual machines with competitive performance on bare metal. In fact, we observe that the largest contributor to the runtime overhead of existentialization is the cost of allocating objects whose size cannot be determined at compile time, which can be optimized with careful use of the stack. In summary, we make the two following contributions. We give a language-agnostic description of existentialization, identify some key challenges, and comment on possible implementation strategies depending on the source language and the compilation target. We report performance measurements comparing existentialization to monomorphization. Background: boxed versus inline representations. How big is that? It's just 10 line. It's just like 10 pages here. This section introduces some general background on object representation and binary compatibility. In managed languages, an object is typically represented as heap allocated structure that contains the field of the object along with the header containing runtime information about the object. The contents and layout of a header vary from one system to another, but in general it comprises the type of the object, the size of its payload, and a table mapping a virtual method to their implementation, aka vtable. In Scala, for example, these elements are stored in the class metadata, referred to by the header. Hi, Ali MSC. Hello. So you have a class vector2, you have a class circle with a field area. So you represent in Scala, you have some mark, then you have the class. So like which class is this object is stored inside of the object. Origin, whatever that means. Oh, origin is the vector2. And the radius. What is 2.1? Is that the radius? Origin, mark, class, 1. Yeah, I guess. And so this is 8 bytes because this is a pointer to this structure, right? Makes sense. In Scala, for example, these elements are stored in the class metadata referred to by the header. Figure 1 illustrates showing the in-memory representation of a simple object graph. You're bad cop. A raid! Wait, what were you doing on today's stream, Bad Cop? I glanced a little bit, but I didn't understand what you were actually trying to achieve. Hi. Can I share my channel with you, sir? I am new here and I want to share it with you. Alright, sure. That's your channel over here. Your stream crashed. Yeah. It looks like your stream crashed, Bad Cop. Wait, what is this? Alright, so I don't know what you were doing, but I am trying to make a programming language, and I'm reading right now the paper. I don't know why, I never read papers, but I don't know. This paper is called Existentialize Your Generics, which is the alternative to dynamic dispatch and monomorphization. Right? So right now I'm not really compiling my program. I am only having the interpreter. But even although we are only having the interpreter, I am still right now technically doing monomorphization. But I'm doing monomorphization every time I call the function. So I'm like monomorphizing on demand every time from scratch, which is why I have performance problems. So yeah, it's a little weird. You're looking at phishing code. How did it look? What did it look like? Did you? Oh, you were trying to like change your phishing game into something else. The evolution of phishing. What did you end up with? Not sure if it's sarcasm or bot. I don't know. It looks like a bot. But yeah, I don't know. You know what you know what my thinking is though? You say phishing, but you know like what is what goes well with fishing? Racing. Like imagine fishing and racing. So like fish and they race, you know? I think that sounds pretty good. So you should think about it. Yeah, you know, like, imagine a salmon, like, riding a bike or something like that. Alright, where did I stop here? Where did I stop? The box at the top depicts an instance of a circle. This is the memory representation of the classes in Scala. Representation of Scala objects in memory. The mark word contains various information about the instance, notably the identity hash and the metadata for garbage collection. The class pointer refers to another object describing the class of the instance, which, among other things, documents the offsets and alignments of the class fields and contain the class methods. The next segment of the box at the top contains a reference. The next segment of the box at the top contains a reference to the object encoding the origin of circle, which represented similarly. Notice that the radius of the circle as well as the two coordinates of its origin are stored in line as they are primitive values. Yes. One issue with this traditional representation is that reading the origin of a circle requires one pointer in direction. In low latency applications, while the accumulated cost of such indirections can result in prohibitive runtime overheads. Further, the headers associated with each instance may also amount to excessive space overheads. I kind of wanted to implement recoloring a fish at some point, but it sounds hard. A recoloring a fish. In your fishing minigame? Or in summoning? In figure 1, for instance, what did I click? I clicked 1. In the minigame. Boom, 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 boom. Wait, isn't your minigame like just, isn't that just doable with CSS? Isn't that what you do anyway? Or is that a Godot thing? How is it implemented currently? Can you not like replace colors with CSS? Hold on, CSS color key, is that a thing? Color keying. Can we have a chroma key technique using plain CSS or jQuery? Yes, of course. These are the two alternatives, CSS and jQuery, of course. The answer is no, not even with CSS3. If they were all the same palette, it would be easy. I would expect to to do a separate texture. I mean, so when I was doing something similar, you just have a separate texture, which basically tells you which of the which portions should be recolored versus which portions of the texture should not be recolored, like a mask, right? And then you do something with it. I don't know how to do it with pure CSS though, or even with like Canvas APIs without writing a custom shader. But maybe possible, I don't know. But yeah, by the way, the reason I'm looking into this is because the performance of my programming language. So like over here, this is me running my Advent of Code 2025 day 1 on the actual input, and it works really slow compared to the actual like if I just use the previous version, then this is how fast it works. It like solves the entire thing in 1.5 seconds, which is still very slow, by the way, compared to like a normal programming language like C++ or whatever, right? But this over here, I literally just made my programming language like 1,000 times slower by implementing some other features. So I need to look into ways. One of the ways, like literally doing compilation, not like transpilation, but maybe I can just make my interpreter faster. I don't know. Finding better way to for monomorphization. Yeah, the idea is to skip, like ideally I want to skip monomorphization altogether, because monomorphization means bad compile times, and that's really bad, right? I want the compile time to be good. At least like at first I'm going to focus. What did I just do? What did I do? What did I do? Okay, well, this is yellow now, but yeah, eventually we will target like native code and do monomorphization and like LLVM and whatever, maybe, but for now I want to focus on good enough speed and fast compile times. In the context of generic programming, this more efficient memory layout pairs well. Wait, hold on. Consequently, to avoid these costs, system programmers prefer laying out all the data in contiguous regions and dispense with headers. In Swift, for example, an instance of circle would be represented as 3 contiguous floats only, as shown in figure 2. So that's how it's represented in Swift, right? The circle is just the 3 floats, which makes sense, right? That's what we want. In the context of generic programming, this more efficient memory layout pairs well with monomorphization, since the compiler has full knowledge of the information related to circle and its parts during code generation. When doing separate compilation, however, the compiler lacks a closed world view, so it must carry enough type information across module boundaries to perform dynamic dispatch at runtime, hence justifying a boxed approach. So like when you create like a library in C++, it cannot use generic interface if you use dynamic like library, right? I mean, you can not use generics, right, across the thing. And in Rust, the generics, they are being instantiated in the user's code instead of the library's code. And when you do it across modules, which may result in instantiating the same thing multiple times, as far as I remember, right? Resilience boundaries, modern applications. Check out your stuff. All right, what do we check out though? Badcop, any links? Or did you want me to check out the POG emote? That's my emote though. Do you ever play Cave Rim 2? I don't remember. Oh no. Cave Rim 2, Bad Cop. Alright, Bad Cop wants us to not read, but to play Cave Rim instead. This is a reading game, is it not? I mean, as much as I am trying to do the reading here, you know, I'm not the one of the reading. You don't have to play it. Okay, what do we want me to do though? No, I mean, I saw other people play it briefly, so maybe there is no reason for me to play it anyway, right? Like I don't know all of the details about this game, but I know something. It's a listening game, right? Because everything is voiced. How about we do the beat golf instead? Hello, Just. How you doing? Oh wait, hold on. I solved everything with perfect score. Compress Ds. Is there any new stuff? Are people still playing this? 2023, 2024. Can I sort by date? 2025. Type event. Where? Oh, choose your algorithm. Oh, look. It's me. What does it mean, though? That's from the score chasers. How do you go back? Still works. Quit. Quit. How do I quit? All right. All right. Let's try something where we don't have to think instead. What's the next game jam that you're going to be doing? Is there any new game jam soon?
Why and cross the road to get to the firm and
I'm bad.
stop at firm.
Hold on. Big mode is happening again?
What do you call them as helpers? Subordinate clauses.
No.
I had to stop telling fart jokes.
I had to stop telling fart jokes.
Someone told me fatty and
Someone told me they stink. Alright. Good one. Can I go back to reading? Unless you wanted me actually to check something out. Alright. Let's see. Resilience boundaries. Modern applications often involve a large amount of software designed as modular, reusable libraries to speed up compilation times and, perhaps even more importantly, to support individual component updates. It is desirable for libraries to maintain application binary interfaces compatible with the previous versions. The most obvious requirement is that it should be possible to modify the body of the function, for example, to fix a bug, without requiring changes in the client's code. A more complicated requirement is that it should be possible to modify the implementation of a data structure under the same constraints. To illustrate, imagine that we decide to publish the Scala code shown in figure 1, which is this code, right? We just define the struct vector and struct circle. And we define the area for the circle, right? We decide to publish this. Making the change below to the class circle would not be binary breaking change, meaning that any software compiled with the original code could be linked against this new version. This is just adding the scale var, whatever that means, like a property. Doing a similar addition would be a breaking changes Swift unless the original code was compiled with support for library evolution enabled, as it would modify the size of the struct. Similarly, the modifying the order in which the properties of a circle are declared could also constitute a breaking change. This problem does not occur in Scala because the contents of the class is box and therefore the layout is not part of the ABI. To support changes to the contents of a data structure provided by a library in a language using inline representations, one must ensure that clients of that library do not emit code that depends on the specifics of a particular memory layout. Instead, clients should obtain information about sizes alignments and field offsets at runtime and use pointers to exchange data across libraries. Have you read my white paper from 2017? Any papers on the GitHub? Maybe it will compile to Cinecore VM someday. Did it compile? Wait, when did you do this one? 3 years ago? Flappy Bird in the terminal? And it's not in Bash? Look at the code. Yeah, it's also code golfed. So you just see flap here. Yeah, nice. Oh, look, my wait, hold on. My day 1 of Adventure Code is still running here. It's been like an hour of stream already. So we need to like have the alignments and field offsets at runtime and use pointers to exchange data across boundaries. Remark that there does not exist a universal definition of what precisely constitutes a software library across different programming languages or even software project. Hence, in the context of Swift, ABI compatibility is instead described in relative to resilience boundaries, which are defined explicitly in package manifests. Existentialization. This section introduces existentialization by means of a running example. We start with general principles and close with a few observations on additional features that can be built on top of it. Encoding type metadata. The central idea of existentialization is to provide the information necessary for allocating generic data structures and calling their methods without access to their implementations ahead of time and without altering the representation of concrete instances. The first part of this problem is orthogonal to parametric polymorphism, and thus we can set type parameters aside for the moment. One way to conceptually understand the task is to start from a classical boxed representation and factor relevant information out of object headers. Looking at figure 1 over here, we observe that the headers contain two kinds of data. The first, stored in the mark word, relates to the associated instance specifically. Whereas the second, referred to by the class pointer, relates to all instances of the type. Given that we are concerned about abstracting over types, we should focus our attention on the latter. Memory layout. In order to determine how to allocate memory for a data structure, we first need to determine its size and alignment. In our running example, this information is simply contained in the class metadata. If the source programming supports direct field access, then type metadata should also describe the memory layout of each stored member, which can be done by mirroring the structure of class contents. Naturally, other sorts of types should also describe them. Hold on. If the source programming supports direct field access, then type metadata should also describe the memory layout of each stored member. Yeah, I guess. Which can be done by mirroring the structure of the class's contents. Naturally, other sorts of types, for example, some types, arrays, etc., may require other kinds of layout descriptions. An alternative approach to support field access is to generate getters and setters, theoretically trading speed for memory. Runtime sized types. Some programming languages support types whose size is only determined at runtime, such as variable length arrays in C. Perhaps surprisingly, supporting them does not require any particular consideration during existentialization. In fact, allocating new memory for any generic type requires runtime size allocation in the compilation target. Stack allocation remains possible on systems supporting low-level instructions for manipulating the stack pointer. I mean, yeah, if we can manipulate the stack pointer, that's how we do allocation. On other systems, is there some systems which don't support, which don't have instructions for manipulating the stack pointer? Like, I guess you cannot modify the stack pointer, maybe like in WASM or something. Maybe. I don't know. Primitive operations. We should finally encode primitive operations which are universally... Hold on other system, a compromising strategy is to use a fixed size buffers large enough to fit most values and default to heap allocation otherwise. We should finally encode primitive operations that are universally supported for all data types, such as assignment, copy, and deinitialization, and have compiler-generated definitions handling internal implementation details, such as pointer tagging on small object optimizations. In monomorphic context, the compiler can simply generate the appropriate code depending on concrete type information. I think I'm lost. I think at this point I'm lost. My attention span is too small. I cannot read papers like this. This is only 10 pages, but I think I'm lost. Let's see. I'll try to follow here though. Here's an example. The following snippet shows a possible implementation of the type metadata for a vector type, similar to that of figure 2. Using C++ as compilation target. C++ as compilation target? Okay. So we have... So we store the type information. Type needs to know its size. It needs to know its members. We need to know how to copy the type and how to drop it, right? Okay, sure. So float is of size 4. Implemented using trivial copy, trivial drops. Okay, sure. Type represents the metadata of a type. It describes the size of an instance. So we actually like store this at runtime. Is that what they are saying? So we don't do full type erasure. Using type metadata. Existentializing a generic function consists of replacing the type parameters by term parameters, accepting type metadata, and replacing operations that depend on a generic type parameters by operations that depend on these additional term parameters. So to illustrate, let us start with the following definition of the polymorphic identity function in Swift. So we have function ID, which takes type T and returns T, right? The first step in existentialization is this definition is to replace the generic type parameter with the corresponding term parameter. So we actually have the type T as a runtime argument, right? Yeah, okay, I think this is literally my idea then that I had. I shouldn't. I should just stop reading papers. All of my ideas are already like what I end up reading. I don't know. Notice the function's result is written to a pointer. Wait, hold on. But ID has a result R and X. So yeah, okay. So because we cannot return the generic type, right? Like, how do we return the type whose size we don't know, right? That's the question. It means that the like, who is allocating the memory for this? It's the caller's basically. It's the caller's responsibility to allocate the memory for the return value of a function, and then we pass the pointer to the result into functions, right? And so we copy the into the result, like we assign the result to something. Yeah, okay, that actually makes sense. I guess I don't need to do this if I transpile to language like JavaScript or whatever, but if we compile down to C, this actually makes sense. Or, I mean, to native code, whatever. Notice that the function's result is written to a pointer taken as parameter rather than returned like the original definition. The reason is that the type of size t is unknown at compile time, and thus there is no way for the compiler to determine how much memory ID should allocate. Instead, this responsibility is transferred to the caller, which has either access to type metadata that can be passed along, or knowledge of the concrete type for which ID is instantiated, and thus can provide the appropriate type metadata. Yeah, so like it basically either already has the metadata or it can figure out the metadata, right? Yeah, sure. Which means that it has the access to the metadata, that's all. Remark that this encoding satisfies the requirements of the resilient ABI. Since ID is not monomorphized, its body can be modified without requiring any change at call size. Meanwhile, it makes no assumption about the memory layout of its argument or the way instances should be copied. Yeah, but at the same time, we always pass all of our arguments by pointer, so there is like pointer chasing still happening, right? So yeah, but this is pointer, not necessarily to the heap, I guess, right? And this only needs to be a pointer for generic types, right? For concrete types, we could have it be like be not behind a pointer. I suppose. Penguin operator, hello. So its body can be modified requirement without requiring any change at call sites. This is also good, basically, right? Like, the reason we want this is, like, once again, for fast compile times. This means, right, like, because of resilient ABI, it means that we don't need to recompile the entire project if we change some code in one of our dependencies, right? If we only change like the implementation details that we don't expose, and we don't need to recompile the things that depend on the thing, which is good for incremental compilation, I guess. Furthermore, the existentialization of ID can be used with any arbitrary type without involving any code duplication. Generating type metadata. The previous example, you have used the type metadata constructed statically as global variables. It may, however, be necessary to generate new instances at runtime. Yes. Since the set of all types possibly instantiated by a program cannot be enumerated ahead of time in general. For example, consider a simple function swapping the elements of a pair. Function swap, right? Yeah, the existentialized form of swap requires the metadata of the type pair ut to handle the result of a make pair, which is constructed from the metadata of t and u, right? So like we have two generic arguments here. So we will have two runtime arguments. We basically have the metadata of the type t and metadata of type u here. But the argument that we actually take in is the pair. But we can construct that metadata if we know these metadatas. There is no way for the compiler to determine all possible values for these parameters ahead of time, and thus the metadata of pair ut must be determined at runtime. It may be desirable to ensure a one-to-one mapping between a type and the instance representing its metadata to amortize the cost of creating new instances, curb memory overhead, and support fast type equality. All of these goals can be achieved by interning the metadata by means of a hash table maintained by the runtime system. Yes. Like, I literally was thinking of the same thing before, like, reading this paper, like, a long time ago. Is this like a new approach? I mean, it's used in Swift. Oh, no, hold on. That's not used in Swift. This paper itself is like from 2025, from October. Though. Incidentally, this approach also circumvents a crippling issue of monomorphization, namely the inability to process recursive functions, nesting type arguments in structural types. I'm not sure what this means. The inability to process recursive functions, nesting type arguments and structural types. For example, the program below cannot be compiled in C++, although its equivalent in Java would have no issue. We have a generic function f, takes t and n. If n is more than 3, then return 0. Otherwise, we return f, make pair a and 1 and n plus 1. And then we return f 1 and 0. Yes, okay, yes, because like this like creates infinite amount of like monomorphizations, right? Because every time we monomorphize a function, it calls another function, and it monomorphizes recursively, creates a new type, and we have infinite amount of types, right? Makes sense. Okay. The call in main triggers the monomorphization of f, demanding a copy, substituting t for int. Then recursive call demands a substitution, right? Thus, monomorphization never terminates, even though the call to f1 would not diverge into runtime. Existentialization sidesteps this issue completely because only one version of the function will be compiled, while the type metadata passed down to each recursive call to f will be computed lazily at runtime. So far, we have avoided the problem of dispatching arbitrary user-defined methods at runtime. Unlike the class metadata of Java, the type metadata that we have presented do not contain a method table, and thus additional information is required to support dynamic dispatch. The two approaches can be taken depending on the source language. If the methods of a type form a closed set that can be enumerated by looking at the type's definition, as in Java, then one can simply store virtual method tables in type metadata, provided that each entry is either monomorphic or existentialized. Otherwise, one can rely on dictionary passing, taking expression from systems supporting type classes. Yeah. The difference between like type classes is that we can create a new type class. So we can create a new method for the type outside of its definition, or which is why we need to pass the dictionaries, right? We illustrate the later technique below with the following Swift program. We have protocol shape, which allows us to construct the area. Function smallest t implements the shape protocol. We have two t's. We return t. We want the smallest one. Alright, so we introduce a type class, a trait in Rust, describing an interface. It is used by the generic function line 4 to constrain its generic parameter, and thus ensuring that calling x.area is well typed in the body. At call side, the compiler must provide an instance of this class for the type, which with which the function is instantiated. Right, so yeah, basically we have type classes, and when we need the so this is the type, and type implements the type class, the trait. We are going to pass the implementation of a trait as another extra argument. So I guess in addition to the type metadata, we provide this implementation as an extra argument. Once again, right? So we have a smallest, right? Yeah, there we go. That's literally what they do here. The smallest is the function. This is the return value, pointer to the return value. This is the first argument, the second argument, the metadata of type t, and the implementation of a trait. Yeah, that makes sense. Okay, do I even need to read this? I mean, we're halfway through. I think I can read this through. Maybe there is some useful thing that I have not thought about. As we have discussed, functions like id or smallest write their result to storage expected to have been allocated earlier in the call hierarchy. If such an allocation is for a concrete type, we can allocate a fixed amount of bytes on the stack or the heap before passing a pointer into the existentialized function, as in the example from section 3.2. However, if the allocation is for generic type, then its size can only be determined at runtime using some type metadata. For example, consider the following Swift function, total area. This is not very academic. This paper is understandable by programmers, I guess. That's not like homotopy type theory or something like that. This one is really easy to understand, I think. The following Swift function, total area. We have the list of shapes, right? We want to return the total area, so we need to like add the area, right? So over here we are calling the area method, and we don't want to monomorphize this function. So how do we call this, right? We need to allocate. Wait, what? Wait, what's the problem? Because the area returns the float anyway, right? In the protocol, yeah. The expression access I. Oh, I guess access I like us. Okay. Maybe like maybe the problem is this indexing. Subscript accessor of Swift array type. There is the return type of this operation is an instance of t, right? So like, yeah. Although like they say the return type of this operation is an instance of t, but that is not exactly true, because the indexing operator in this case just needs to give us the reference, right? We are not trying to copy the element, because this over here is a place expression. You haven't seen me read one before? I tried to read the homotopy type theory on stream before. No, that one we rage quitted. at some point. The expression access I is this, right? So like, does Swift not have Swift place expressions? Prefix expressions, in-out expressions. Try operator. Or do they not have like L value? No, I guess like they technically do have that, right? They do have L values.swift. Move semantics. I don't know, but maybe like but let's say that in Swift, for some reason, the indexing actually returns the copy of the element at index I, right? So the return value of this operation is the instance of t, which is generic in this context, right? So like how much size in memory does this hold, right? This is a generic type, so we don't know this. In order to allocate this, we have this stored in the type metadata though, which is available to us, and so we must allocate we must allocate size described by the metadata. Yes. But we still can allocate on the stack by modifying the stack pointer if we have that operation available to us in the target architecture, I guess. That's what they were talking about. Another interesting aspect of this function is that the iteration over the indices of access also involves a generic operation, namely the call to count. Since the type of access itself is generic, T is sugar for array T in Swift. This method count is defined by the collection protocol to which array conforms, and thus we must obtain an instance of this type class as shown below. Since Swift adopts global uniqueness of type class instances, we can construct. So like, hold on, they say global uniqueness of type class instances. So Swift does not have the orphan rule from Rust. They only check it like globally when you compile a binary. Is that how Swift works? We can construct one directly in the existentialized form of total area without adding new parameters. So total area, we have XS, T shape, this total area. So yeah, we don't have the metadata of the hold on. You also dev your own programmer Rangsbrak RC. Penguin operator. You meant to say programming language, but then your cat jumped on your keyboard or something. Oh, it's just German? Okay. Compiled statically typed low-level programming language made for Linux native games for Game Jam. Nice. Is Jam over? December 20. Did it 3 days ago, but this thing was over 1 week ago, more than a week ago. You were late. Your last commit is Lexer. Are you making it or is it working? This looks like you have the Lexer and you don't have the parser. You just started this, right? You just do tokenization currently. Nice. Well, that's how you start making a programming language. Good luck. All right. So what are they saying, right? We don't have the metadata of the thing itself, right? Of the count, right? This over here, C count, right? So what is C? C is array is collection T. Okay, so basically we have the metadata of the type T, and we can basically get this over here. Basically gets us the metadata of C, or I guess no, it gets us the implementation of the collection protocol of the array type, where element type is T, right? We just get this by doing the metadata. That makes sense. So that's how we know how to where the count method exists. Sure. Line 4 retrieves the witness of array T's conformance to collection, assuming the existence of global a function implementing the construction of such type class instance. So basically, I think it's something like this. When we say that we implement a trait for a type, or a protocol for a type, I guess, right? This automatically creates this function. So every implementation of a trait is this, right? So that we can get the vtable based on the type metadata. Yeah, that makes sense. And then this is this can be like interned and whatever. Yeah. I can see how this still has like the runtime cost, so but this should be good enough for the debug builds. That's what we want, the compilation speed, and this should be fast enough for sure. I pressed something. Where are we? Dynamic dispatch. This assumption is justified by the fact that Swift enforces a global uniqueness of type classes, meaning that types can conform to a protocol in only one way, globally in a language, supporting local type class instances, e.g. Scala. This witness should be taken as an additional parameter instead. In a language supporting local type... Wait, hold on. Scala has local type class instances. Yeah, this witness should be taken as an additional parameter instead. What witness? The witness, which is the implementation of the type class, because there are potentially multiple implementations of the type class. Yeah, okay, that makes sense. Yeah. So that means that, yeah, we might not be able to do that. Okay. Yeah. Which one do we want? Do we want local trait implementations? I think probably. But what if we use like multiple protocols on the type? Like there's an explosion of the amount of arguments then, potentially, no? Because this right now over here, this corresponds... Well, I guess in Scala you would well, I mean, array, like, it's because this is implemented through a protocol, right? The collection is a protocol, but it does not have to be a protocol, because arrays like might just be concrete types, and this is just their like method and stuff going through the protocol, whatever. Yeah, it depends. Right. Finally, line 10 cleans up each copied instance. E, allocate t size. E is allocate t size. C at E, right? Yeah, so we are indexing into XS and index I when we store the result at E. So in order to store the result, we should have allocated it. But this allocation is technically could be done on a stack, right? We omit the handling of alignment requirements for brevity. Yeah, there's also like alignment or whatever. But yeah. So when you allocate, you need to not only know the size of the type, but also the alignment of the type, right? Because that's not the only like thing that is needed. Whilst our examples have focused on supporting independent value representation, existentialization is not incompatible with sharing and managed pointers. To illustrate, let us consider the problem of representing a managed buffer of arbitrary length. One way to implement such a data structure is to tail allocate. Let us consider the problem of representing a managed buffer of arbitrary length. One way to implement such a data structure is to tail allocate the buffer behind a header consisting of a reference, counter, and size, as shown in figure 3. As the most common operation one performs on a buffer is to access its element, it's convenient to keep the address pointing at the start of the tail allocated contents rather than the start of the header. The latter can be computed with a simple subtraction, sure. The following definitions describe how to construct the type metadata of the data structures, since an instance can be represented by storing the base address of the contents, size, blah, 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 blah. Rather than copying the bytes of an instance, the copy operation simply increases the reference counter in line 5 and copies the box pointer. Notice that H, so yeah, managed buffer, when we copy it, we do like, yeah, okay, reference counting here. Okay, sure. It's just like an RC slice. More efficient garbage collection mechanisms are obviously possible. The takeaway is that the ability to customize primitive operations to be leveraged to support compiled defined behaviors in generic contexts without requiring uniform representation of all data types. Yeah, I understand. Okay. Type reflection for free. As we have briefly mentioned in section 3.1, type metadata can be leveraged to support reflection by allowing the user to consult their contents. This observation is actually not at all surprising, considering the fact that looking at existentialization through the lens of type classes, type metadata can be understood as witnesses that types are types. On the most common type reflection feature is the type test, for example, which is the ability to inspect the runtime type of a value at runtime. Type tests are often used in conjunction with pattern matchings, as in the Scala below. The function is to inspect the type of its argument to evaluate different expressions depending on the type. Def2 is to v is t v match. If I is int, then I is equal to 2, and if s is string. Wait, can you actually do that in Scala? Perhaps surprisingly, uncommenting line 4 with the result. Uncommenting line 4, this one over here, O option int is always equal to sum 2. Uncommenting that will result in a warning complaining that type arguments cannot be determined from the signature of is2. This limitation is consequence of type erasure of the JVM. Oh yeah, because in the JVM, when you have the generic class, so option T is like the generic thing, we don't actually have this information stored in the JVM, right? Yeah. You're not affiliate anymore? What do you mean? Am I not? I don't know. What do you mean? Twitch isn't showing you all the usual stuff. I don't know. I think everything is working.
Question mark.
Question mark. Do 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 do. All right, and hello, Devninia. By the way, we are reading theory. Can you imagine? Although, to be honest, this is almost useless because I was thinking of implementing this before I knew this paper existed. I just saw this today, posted by the anti-programming language developer.
Mark question.
Swift. It's not about Swift. It's like references multiple languages, or here's Scala. And stuff. Okay, so this is the problem of the JVM. Although Scala supports parametric polymorphism, type parameters are ignored on the JVM, which relies only on subtyping and dynamic dispatch. This strategy simplifies the bytecode, but also comes at the information loss at life and runtime. It is not possible to recover the arguments of the type application in general. We don't care about that. Java. This issue could be solved by existentializing is2, as that would translate a generic type parameter into a term parameter rather than erase it, since this parameter is meant to identify the type, which is2 has been instantiated. We could then simply check whether its value is equal to the metadata of another concrete type to perform a type test as shown below. The call to metadata returns the runtime description of option int, which must be distinct from that of another application of option. Sure. Evaluation. This section reports how existentialization fares against the monomorphization by comparing the runtime performance of synthetic micro-benchmark. Yes, like we see a lot of pointer indirection and a lot of extra arguments to function, which means that it should be performing worse than monomorphized stuff, for sure. Shows Swift because it implements existentialization natively. And C++ and Rust because both provide low-level primitives that allow us to emulate existentialization manually. To broaden the comparison, we also included two JIT-compiled languages, Scala and JavaScript, to assess whether JIT optimizations can mitigate the interaction costs of existentialization. We start with the description of our benchmarks. Okay, whatever. Monomorphized, a partially existentialized, fully existential. All right, so it looks like in Rust we get twice slower. What does partially means though? I'm not sure. Area partially existentialized. Oh, because it still says like vector t shape, and over here the shapes is also iterable. I see. So we take anything that implements the iterable interface, basically. All right. I see. I understand this. Conclusion. We started extensionalization, a technique first implemented by the Swift programming language for the separate compilation of generic functions and data structures. Unlike traditional approaches to dynamic dispatch, extensionalization does not rely on boxing, thus supporting efficient inline data representations. Instead, the information necessary for allocating generic data structures and calling their methods is passed down separately in a style reminiscent of dictionary passing on type class oriented systems. We have explained extensionalization independently from its original implementation of Swift. Yeah. No, this is nice. This is nice, but once again, I had the same idea before. Basically, so over here, right, we have a generic function add, right? How do we add the things, right? So technically, the way our generics work already in the interpreter is that this is basically a function taking the type as the argument, and this returns a new function, right? This returns a new function. Let's say that I was transpiling this to JavaScript, for example. Yeah, I guess like transpiling this to JavaScript. How do we transpile? I think I do something like this. Then we say that add is a function that takes t, which is a type. All right, so function add takes t, and it just returns the function which takes a and b and returns a plus b. I don't know, how do you do this? Like this, I guess. Like in this case, that I mean, because this is native, right? But I guess technically add, this should not be native, right? Because this should be that t implements the yeah, I don't have like a way to do this yet in my language. So we basically are assuming that it's implemented for all of the types, but we should basically say that this, I think my syntax will be something like this, where we have t as add, where add is like the trait or something like that, and then over here we would like use it actually. Right? So this is going to be another hidden argument. We have the type t. I'm not sure if so this type is still not going to be used, but this function over here that we return from it, function inner a and b. Raymarch, hello Raymarch. Did you just join? Hello. Hi. So we just return this inner function here, basically. Yeah, but this is having an extra argument, this one, which is t as add, and then we just over here, this is going to be like, I guess, t as add dot add a and b. That's how we like add things together. So we just we literally just transpile it to this. I guess. In this case, the type itself is not used at all. It would be used if I was transpiling to C, because that would store the size metadata and stuff. But basically, we're reading Raymarch a thing which is called existentialization of the generics, which is instead of dynamic dispatch and monomorphization, the third approach, which is used by the Swift programming language. Should not you then write as add.add? You do not need t here. Over here, I don't have like this implemented yet. I mean, no, I do have this implemented. It's just because I cannot find add in scope. Hold on, we just do this. Add is self type. Add is self and self into self. I guess I can like actually make this available in my thing. It's just like this over here is not checked right now. This is this is parsed, but this is not checked, right? So when I call the function add, I can call it, right? But obviously I have not implemented this. So if I try running that, cast examples, hello, right? This is going to say that there is no implementation of int32 as add, right? So this is not checked currently. We need to implement int32 as add to be add is std of add int32, I guess. All right, and then we add 2 plus 2 and we get the 4, right? But yeah, basically what they did, Raymarch, is here's the summary. The summary is that your generics get converted into functions that actually take the type. So you don't do type erasure. You still have type metadata available to you at runtime, basically, right? So when you have a generic function like this ID, this is a hidden argument to your function. I mean, this like maintains being the argument of your function at runtime, and this is what stores the metadata of the type, including the size and how to copy the type, how to drop the type, and the members of it. Everything here is passed by pointer, but this pointer can point to stack easily, so you don't actually perform the allocation, you don't box every element like every data. What makes that different from dynamic dispatch? Well, I mean, it is dynamic dispatch, but what makes it different from normal programming languages which do dynamic dispatch is that it does not require boxing. Because it stores the pointer to the v table, basically not inside of the value itself, right? And like the type information is not encoded in the value itself, but separately, and is passed as an extra argument, something like that, right? Yeah. So I don't think I should like have this type argument as actually like this. I think we can actually transpile this to JavaScript literally like this. The only thing that we want, maybe like this over here in JavaScript creates a new function, I guess, so we can like intern this because it's a generic, so when we call this with multiple times it should return the same type or whatever. So fat pointer. Yeah, I guess it still is a fat. I guess this still is a fat pointer. But I guess there's a difference in this other example. What example? What example is good here? It's better because they share the x and y. Yeah. And also like the like one pointer can just point on the stack, not necessarily on the heap. The second pointer to the v table is shared across the types. And also here's the other example, right? Where was I? Like over here, right? This is C++. You are trying to make a pair. Or no, let's swap, right? The function that swaps the pair of t and u and returns the pair of u and t, right? So this just needs the metadata of t and u, and it can construct the metadata of what a pair is at runtime. It does not need to construct the metadata of this at compile time. If that makes sense. Alright, anyway, let me just link this here if you're interested. Iron Blade Warrior, hey, what are you coding, mate? Hello, mate. I'm making a programming language. So I was just reading the paper about existentialization, which is how they implement generics in Swift, apparently. And I think I might use the same approach so that the compilation is fast. Right now I don't have any compilation at all. Right now I'm having the interpreter, but my interpreter is suffering from performance issues. What's there to hate about programming? It's magical and fun process. Yeah. Yeah. I guess I should have added that I hate programming languages, which is why we're making our own programming language. Right? That we will definitely not hate. No one will hate my programming language when it actually is fully done, which is probably never, but you know. Monsters Dev. Hello, happy Christmas. How's it going? Hi. It's going well. It's going well. So yeah. Right now there is like a problem. Like I solved the advent of code with my programming language, and if I try to run with the current version of the programming language, the advent of code day 1, then it runs 1,000 times slower than it was running when I was actually solving it. So like this is 2 different versions of my programming language. This one is still running, this one is already done in 1.5 seconds. So the problem once again is that I'm kind of doing the monomorphization every time during evaluation. I'm monomorphizing every function every time from scratch when I call it, which is absolutely wrong. So yeah, maybe I can fix that by doing something. One of the things is that there are 3 kinds of programming languages: the one people complain about, and the one no one uses, and then there's Cast. Yeah. The compiler is part of the runtime. Wait, you're just going through my old Rust version. Yeah, why are you going through my old Rust version? I have a new version. Is it like Lisp? My language, it is kind of like Lisp, yes. I have the interpreter. Interpreter is interpreting compiled code, but I mean, it's not like Lisps are usually dynamically typed. My language is not dynamically typed, it's statically typed. I mean, what do you mean is it like Lisp? There's no like excessive parentheses in this code, is there? But it is like Lisp, I guess, in some sense. I mean, it is like code is data. Yeah, code is data. So yeah, I get the idea for the future, not for a long time, but for the future, the idea is that you should be able to write the compiler yourself by inspecting the code, because you have the code as data. Yes. So like you just have your like function add, and you say something like, you know, like compile add, and you you like get as like the result of this, like whatever, you know, transpile to JS, and you can like run this at comp time, and you can store this in a constant. Like the idea that I want is like I want to transpile my shaders written in my language to like GLSL, for example, here, for using those in games for shaders, right? And we just convert the function into a string. I mean, this is obviously should not be an add function, but some actual shader, but you know, at least based language to transpile to. I mean, I don't have any other alternatives really. Like, I mean, unless I change my target. But the GLSL is something that I know, right? I guess like what do we actually use these days? SpearV. We can do that at compile time, I guess, too. But SpearV is not usable everywhere, which is why I am probably still going to use GLSL, because SpearV is not usable everywhere, right? But I mean, technically it's maybe is available everywhere. I don't know, like you can you use SpearV in browser, in WebGL SpearV in WebGL 2, can you do that? I think you still have to do GLSL, right? But there are SpearV to GLSL compilers, right? So we can go to SpearV and then like invoke the SpearV to GLSL compiler, right? But I mean, why don't we just go directly to the this one? All right. Yeah. Well, I mean, ideally, we can do everything. So, like, it's whatever we implement when we decide to actually implement that. They have a custom language, WGSL or GLSL. Then that translates to SpearV, which transpiles to some direct text thing, which transpiles to SpearV, which transpiles to PTX. Well, I mean, you probably. Like there is like the angle layer, which like this thing, right? The graphic engine abstraction layer, which basically implements GLSL. Like that's how the browsers are implemented usually, right? You do GLSL, but then it translates to like Metal and Vulkan automatically. So like you go the other way, right? You go from GLSL to SpearV, not from SpearV to GLSL when you are targeting browsers. But SpearV to Vulkan is possible. I mean, SpearV is like the thing for Vulkan, I think, right? I wish you liked Slang more. Slang shader. Is that the one by SDL3 or not? There's also the SDL3, right? SDL3 shading language. Is like, do they literally call it SDL shader language? Why am I having trouble finding it? SDL SL. I mean, this is the thing, right? It just says that this is future work, not what the SDL3 uses today. What do they use today then? So then GLSL must be converted to SPIR-V for Vulkan. I think Vulkan can do both GLSL and SPIR-V, right? Vulkan, SPIR-V or GLSL. I think Vulkan can do both. But if you use like some other language, then you would have to transpile. I'm not sure. I haven't used Vulkan myself. Shaders for Vulkan are defined by the SPIR-V specification, as well as the SPIR-V extended instructions for GLSL specification. Whatever that means. Alright, anyway. So what am I going to do? The reason my performance is bad. Is that what we look into? There's also other things that we can look into instead of performance. Or we can just try writing some code in the programming language. One of the things that I wanted to finish is the monad stuff. Did you see the monads, Raymarch? They work in my programming language. We have the do notation like in Haskell. You like this? You seen this? You did not see the monads? Yeah, we can define monads already in the language. Here's the definition. So a monad so we have a higher kind of type as an argument, which is basically a function from type into type. Rust could never. I think technically Rust can do this these days. So with the like Rust monad, you do it with the generic associated types these days. But you don't actually do that, I guess, because there is no practical reason. Because of a lot of syntactical verbosity if you do that, I guess. Can you do that? Can you do a monad in Rust these days? Trait monad. I think this is the only AI-free programming string currently. Everyone else keeps tabbing to ChatGPT. Well, I mean, I am talking to ChatGPT sometimes. Hold on. ChatGPT, allow that you speak about it. Why is everyone using AI? Are they stupid? Short answer, no. Long answer, kind of yes. All right. Now go write something real, preferably in Rust. All right. Let's try to write a monad in Rust. So yeah, a monad is a thing. This takes as like the argument monad. Like you do the generic thing, right? I don't know. Let's call it apply. Apply with argument t. So a monad is basically where am I? It is something like this. You have a function return x. So this is generic t x, which is t. So this returns self apply t, and then you have function flat map, which takes a and b, which takes so like this, I guess, not self, because that's going to be self apply a, and then you have a function f, which is, I guess, impl function from a into b, and then you return self apply b. Right? That's the definition of a monad in Rust. I guess it is possible these days. I think this should compile, right? Well, I mean, return does not work. Let's call thread. There you go. Trait monad is never used. And then you like implement monad for option, but you cannot do that directly, right? So like option family, I guess, is what you do. Where you have like struct option family, right? Because you cannot implement that for like the type constructor directly, but you say that like type apply is just like option t. Return t x t returns option t sum x flat map a b this option t f simple function a b option b. So it's just this map f. Right? I mean, that's how you do it. So this is possible because of the generic associated types, which was introduced. It's pretty a long time ago already, right? For a couple years, I think. (165) on 2022, yeah. Do people actually do that though? Like the problem is that like in order to use it, because you don't have like the do notation and stuff, right? You would have to explicitly say when you want to use like this, that you want to do like option family flat map, right? When you have like, I don't know, sum 1 and function x. Wait, hold on. This is not the correct one, by the way. The flat map, this must be self apply b, by the way. Right, so this should be like returning option b, and this should be not map, this should be like and then. Right? This is the correct thing. But yeah. The monads are also only nice when you have the syntax to use them, right? So in this example, we also define some syntax for the do notation and this stuff, which technically, so like this is just the syntax sugar. This is just the syntax sugar implemented using other syntax sugar. Yeah. There's a problem here though. What's double semicolon walrus? I just like because this is a local syntax, we still have the semicolon, so I needed something that is different. In Haskell you just don't write anything here, right? But we cannot do that because we are not white space in sensitive language. I already used the semicolon for other things, so yeah. I don't know. Well, I mean, technically it's just like I guess this is the operator that is usually used for monads. You have this, we're just composing two things, and you have this operator that is usually used if you are outside of the do notation. What about that? I don't care about the syntax. I'm not going to actually do that. Like the fact that we can do monads is nice, but we are going to use the different mechanisms, right? We are supposed to use the effect systems instead. It just means that my programming language is high level enough that it can encode the monads already, and that is nice, right? Okay, there is one thing though that is not working. This over here. We want more inference. We want better inference. Here's the minimized example of this. The minimized example in the test. Okay, yes, over here, right? We have a over here. We have a monad which just defines the flat map. We define the option here directly. We just don't use the standard library here at all. We just do cast no std examples test like this. Right, so this says that no std is the argument over here. This says that this thing cannot be inferred. So right now I can like explicitly say like option as monad. I think this can be inferred, but I'm not sure. Well, I mean, actually, no, this shows me some errors. Doesn't want to bike shed me even though it's Christmas. You think we should like think about more syntax issues? We can go into that too. Wait, hold on. Interpreter error expected generic. Oh yeah, hold on. Option as monad, not option underscore. There we go. So like this is the explicit syntax. No implementation of option as monad. Oh, I forgot to do that. Yes, implement option as monad is what? Flat map is a wait, what is A? Let's do like A, B, M, A, M, B. I was just trying to simplify this code here, I guess. Flat map A, B, so this takes like A and F, and this returns match A with, if it is none, then we return none. If it is sum A, then we return FA, right? Like just like that. So yeah. You don't want to have to ask the why should like come naturally? All right. So here's the implementation of option as monad. There we go. This works. So what is the type of X here, right? So this is me trying to say flat map. I want to call this function using opt and X into let's say none, whatever, right? So this should return none basically, right? This is a function that takes the option and like applies this function to the value inside of the option if it is sum and whatever, right? Yeah. So right now this just will return none. If I try to evaluate this. But the thing is, we already know that this is an option, right? So this should be inferable. That is what is the missing part here. If I try running this, it says that this cannot be inferred. But it should be inferred. Why should this be inferred? Because I'm calling this function with this as an option. Technically, like this over here also should be inferred. Because we know that this is an option of int32, right? If I say this is an option, this is going to infer that this is an int32 already, right? So this does not need to be specified. If I don't specify this thing, then we just don't know what is the result type either, right? But I guess in this case we don't need to know the type because this is returning none anyway. But because we know that option is an option of int32, I don't need to specify that this is an option. We just know that it is a monad already. And which monad is used here should be inferable. That's the missing part right now. And I need to like understand why this doesn't work. So this is just a higher kinded type inference must be improved, right? So the thing that we are inferring here is not a concrete type, but a type constructor, which is why it is a little bit different, right? What is an option? It's a type constructor. It takes an argument, which is a type. It is already inferable in other places. So, if I have function foo, which takes f, which is like this is the higher kind of type, whatever. And this takes like a, which is f int32, and this should return f string, for example. Somehow just use underscore as implementation. We don't have strings in this no std example, right? So we don't know what the type of foo is here. We can say that foo is taking type and returning type, which is like this. Right? So if I try to call function foo here with this option, then what is the type of this? Underscore. Okay, hold on. So I actually see the... No, hold on. No, that's not the issue. Hold on. Foo. We need to call this using option as argument. There we go. This actually works, right? So because I called this with option as an argument, we know that f is option already. So we know that the result type is an option in 64. So this has been matched properly. But so why is this not matched here? That's the question. We go through the interaction of this as monad. Like, can I make this simpler? This example. Can I make this example simpler? Yeah, let's see over here. This is not inferred at all, right? X, even X is not inferred, even although I'm giving this option int32 as the argument here, right? So we know that in this case, A, this thing over here should be an int32. If I write this explicitly, then we know this. But we don't have to write this explicitly. This should be inferred. So why is it not inferred? Why is it not inferred? That is the question. Is it because I'm going through two generics though? That's maybe the thing. So can I say like over here A, and this takes A? Does this not work then? X. Function is not a type into that. It did not auto-instantiate it. Okay, can I just... let's try to give it explicit arguments here. Like this. Yeah, okay, there we go. This is the simpler... this is much simpler example. This is a much simpler example, okay. So this is a test. I guess I can also remove all of this then. Not really. Let's keep the option. Let's keep the option. Let's remove the monad. So I want this to be inferred. Because I give it option, it means that this over here is option. If I give this explicitly, this will say that it returns an option, right? This must be inferred. This argument is the A, right? This A should be inferred to be int32 because this is an option of int32s, obviously, right? If I give this this explicitly, then nothing changes, really. Okay, so the problem is that I'm going through generics, apparently, right? Let's try to see what is the what is foo underscore. Okay, as you can see, foo underscore, the type of this, we know the generic, but this is completely not inferred. I mean, no, I mean it is inferred that it's a function, but we don't know the types at all. What if I say over here, I don't know, string, I don't know, let's say int32 and f, like that. Is it going to infer? Yeah, it's like this thing is known. All right, can we say A here? Okay, so if I do int32 like that. All right, so why is this not inferable? Oh, is it because I'm doing the substitution potentially? Hold on.
Hello, Nigel Ithro.
Did you get an email thanking you for creating cast? What? An email? Nope. Hello, Nigel. Nigel, you missed the reading part of the stream where we actually were reading theory today. The founder of Clojure did and had a nice rant on GitHub. Thanks AI. I got this email. Rich, your creation of Clojure Psychopathic blather worthy of a third grader's homework assignment to write a letter to a public figure you don't know. Claude. What does this mean? They received the an email by AI. Did AI message the creator of Clojure? I'm subscribed to the cast repo and I get emails like commit pushed one commit HFTGHD. Yeah. I did that earlier today. How about we though actually merge my stuff? This pull request. This functorial stuff was I guess like we can close this one. And but this one is actually going to be merged. Where's the button to merge? Ready for review. Merge. Good. All right, Rob Pike. Like this. This is the co-founder, the co-creator of Go. He was not happy either. All right. Wait, what's the message though that they received? I don't get it. All right. Anyway, I'm too lazy to read about this. So what cast can do now? Well, it can do monads. The monads work now. I just they like one thing is not inferred here. So why were they sending emails now? That's weird. The AI is messaging the creators of programming languages. Thanking them for creating the programming languages, right? All right. Yeah. We want to infer that this underscore over here is an option, because I literally pass it as an argument here. And then this over here is an int, because we passed an option of int. So this underscore is this underscore is that. That should be inferable. Why is it not inferable? That's the question. This over here. FA. So we have this this type, right? FA into AF in 64. What happens when we instantiate this one? Is that we try to substitute all occurrences of F here to figure out the type with the actual argument. The actual argument is underscore. So what we want to see here is not underscore. We want to see like underscore instantiated with argument int32. That's what we want. But we can, oh, I see, but we cannot. We cannot do that. Oh, I see. I understand now. We cannot instantiate underscore int32. This just doesn't work, right? The type here is underscore. There we go. Wait, no, we should be. No. We can't do that. No, we can't do that. We literally can't do that. We just don't know the result of it. So like the fact that this is shown like this is actually correct. But if I will say that this is option int32 into something, okay, so this has been unified, but because now we know that this is an option, because I have type ascribed this here, we know basically that the result of instantiating something with int32 is equal to option int32. We now need to basically say that underscore int32 is option int32, right? Which means that this underscore we need to like say something like this. Let x const please infer underscore. Let x be equal, well, let x please infer int32 is this. Of type option int32. So we know that this is an option, right? Which means that please infer should be noble here. I guess I need to like dbg plurint please infer. And then run it and then see. Yes, so this has been inferred to be an option, right? So that's how this works. If I know the type, I'm unifying them, I'm unifying the type constructor itself. So that should work. What is not working? This over here is already not working. I think I know. I think I know. Maybe. So we have, so we do it in multiple steps, right? First we say foo underscore. All right, so once again, in order to figure out the type of this, we are substituting from the right side here, right, like this. This is the type. We need to replace all f's with this underscore, right? Which is please infer. Can I do let please infer? And do that, by the way, I'm not sure. Oh, there we go, yes. So this actually works, right? If we do that, then this please infer A into that. Okay. Yes. But the problem is, this is a binding. This is not an inference variable anymore. It's a little bit different. How do I debug this issue? Because this underscore is the result of us instantiating underscore with A. That is happening in the interpreter core. Over here, we're doing instantiating. Let's do the info here. Right? Wait, I had something else in my stash. No. Abort. Can I do that? Git merge abort. There is no merge to abort. Merge head missing. I have merge changes. How do I undo? Who knows how to do git? Git undo stash merge conflicts. This just no, that's not what I wanted to do. That's not what I wanted to do, but okay. Discard. Hello, I guess hello world. I don't want that. Okay. Wait a second. Why is this not complaining? No, because this returns underscore, I guess. It's not complaining that this is not, yeah, whatever. Yeah, because I'm not using a trait. That makes sense. So I don't need this type inferred at runtime. Okay. So yeah, I just need to do in the interpreter here. I wanted this to login form. So what are the instantiations that are happening? Right? There's a bunch of them, right? So I am instantiating. Let's get rid of these and get rid of that. Right? So first we're doing instantiation of f with a, f with in64, f in 64, f a. For some reason I'm doing this twice. Then over here, this is my underscore. Underscore is being instantiated within 64. Underscore means instantiating with type A. Option is being instantiated with int32. F with int64. So why is this F here? Why am I seeing F again? And then test foo underscore. Which is this thing. Wait, hold on. Instantiating fa test foo underscore. This is the one that I care about, test foo underscore. And the result type is this. Underscore instantiated with int64 and with a. Oh. No. I think I have an idea, but so when we say foo underscore, right, we understand that the type here is a, which is underscore a into underscore in 64. Let's remove this tuple here. Right? That should be understandable right now. That this is the type. Welcome back, Penguin Operator. It should be understandable that this is the type. But then, when we instantiate this further, because this is a double generic, right? So what is the type of this thing, right? So let's say that this is basically let foo underscore be foo underscore, right? Because that's literally what the type here is. This underscore is that underscore. Let's say const x is underscore. This over here is x. X. That's what we know. Right? But we don't know the result of x applied to a because we don't know what x is yet. So now what we are trying to do is we're trying to instantiate the foo underscore with, let's call this foo x, I guess, right? Foo x, we are trying to instantiate that using int32. That's what is happening there. So when we do this, how do we figure out the type of that? Well, in order to figure out the type of that, we basically take this thing, and then we try to replace all occurrences of int32 here. But we don't actually store the type as xa anywhere. Because we are waiting for this to be inferred, right? Like we're saying here, just underscore. We don't know that a even exists here yet at all. That's right. That is right. So in order to infer what x is later, we need to remember this information. When I apply instantiation to something that is not inferred here, we know that the result must be named. Like we need to remember how we got that type. But here's the problem though. Here's the problem. What if x is not a type? Like there's a difference between type constructors and aliases actually. So let's say that we were using Rust, for example, right? We have struct foo t whatever inside, right? And then we also have this thing called type alias t is equal to foo t, right? The way we write that in our language is almost the same. And so this x, when we infer it, like because foo t is alias t, right? How we must infer it though to the foo t, right? And not to the alias. So what is the difference? Because I guess the inference variable should never be inferred to be that. I mean, yeah. But what this means basically is that like in this case, this is a not inferred thing. But in case it was an inferred thing, right? So like, let's say that we have foo is t new type, I don't know, like values of type t, right? Whatever. And then we have alias, which is t just foo t. So that's how we that's the alternative of that in cast. This creates a new type which stores the name. So if I try to say that something is of type alias int32, we will still well, look at that. We already have the problem. Right, we have the problem that foo is not alias. And why is that? It's because when I'm so right now when I'm instantiating the generic, I basically, and if I know the result, then I'm unifying the generic and the name of the generic of the result, which in this case is not correct. So this doesn't even work. I'm wondering how this works in a dependently typed language, right? Like, I guess there is a difference between a type constructor, I guess, and an alias, right? So right now, the type of foo is basically a function taking type and returning type, and the same is true about the alias, right? We don't necessarily say that this is a type constructor. We don't store this information here. And so I guess like, even although technically a type constructor is basically a function returning a type, it still needs some distinction. Type aliases are often more restricted, except in TS. TypeScript. Let's open Idris. Let's open Idris. So in Idris, we can have a function, right? So we can have alias, which has type into type. Alias t is foo t. So what's the difference in Idris? You say the data foo t is equal to t. Does that work? Couldn't parse declaration. Idris 2. Haskell doesn't let you do recursive types in type aliases. Helix has Idris index highlighting, by the way. Really? But why is Helix? Oh, because I don't have a git in it. Okay, sure. I need to add the git ignore then, because it looks in all of the hidden folders. Gerund, I guess, is what I want. Okay, there we go. And I what is build? That. There we go. Okay, test Idris. Wait, what? No, it doesn't. That is Helix, right? Where's my syntax highlighting? set language Idris. I think maybe because it's wait, what? I mean, it knows the language, knows how to comment things. Alex, health. Tree-sitter parser. Tree-sitter parser is there, but highlight queries is not. Does it mean that it cannot highlight, even though we have the tree-sitter parser? So I have the tree-sitter, but it doesn't highlight. Like, seems like I cannot expand my selection either, though. So I don't know. Anyway, my question is, how do you declare a type? Small examples. That's how you do it. So I guess the problem over here, I need to have foo t, right? Because this is a data constructor. And this should work then. Yeah, Helix doesn't have an integrated terminal, which is why I don't like it. Address to. No, couldn't parse declaration. What? Wait, oh, the argument must be like lowercase. Foo a is a. Alias x is x. Oh, wait, maybe alias is existing thing. I need to say like alias 2. Maybe that's the case. No, couldn't parse declaration. Oh my god. It's a single colon, not a double colon in address. Main foo is already defined. Main foo is already defined. What do you mean? It should have a different, like, constructor should have a different name, right? Can I just say A here, though? Couldn't parse any alternatives. Expect capitalize identifier. Got A. Yeah. It cannot have the same name. Wait, hold on. What? This is annoying, though. Isn't it annoying? Make foo. So, I mean, I understand why, though, because we live in the same namespace, right? What is the type of foo? So yeah, so the type of foo is type into type, right? Same as type of, I think this can be alias. Type of foo is type into type. Type of alias is type into type. So how do we know that this is a constructor and this is not a constructor? Does Idris do the inference for this? How do I test that? How do I test it? Here's what we want, right? We want to have a function f, which takes, so we have first the function that takes type and returning type, right? This should be implicit, so it should be inferred, I guess. And this takes, so this is called like f. This is the higher candidate type, right? So then this returns f int and f int. Does it work? So when I say f, f make foo 1 2 3. Okay, it says cannot solve constraint between foo integer and f int. Question mark f int. Interesting, because 1 2 3 is integer and not int, right? Int is different. How do we make integer and not int? Those are different types. Let's just say integer here. F 1 2 3. Cannot find implementation for num f integer. No, it's f make foo 1 2 3, right? Cannot solve constraints because between foo integer and f integer. Okay. Okay, so Idris doesn't actually do this kind of inference. Idris doesn't actually do this kind of inference. Does Idris have monads and like do notation? Let's ask our friend ChatGPT. Does Idris have do notation? It works for monad, just like you would expect, and it's used everywhere. Pattern matching and do. Be careful with my email, Idris creator asking the question. Okay, so I guess my question is, what? My question is, how does it infer? You know what? Do you think it will understand the cast source code? Okay, here's some cast. Here. What here should be inferred as? Option in 64, yes. Okay. So it actually understood everything, right? So foo is polymorphic over a type constructor f, type into type. It takes fa, it returns f in 64. If you specialize with it, if f is option and a is in 32, so the type becomes when is it figured out that f is option? And how would that work in Idris? Pay attention, this is where type systems stopped being polite and start throwing chairs. Where f is option at application time, left to right, by unification, not later, not eventually. You have this. So this is Idris now. We have f type into type, a is type, fa into f in 64. Now you apply it. Foo question mark x. The argument has type option int 32. Sure. This is my argument, option int 32. So the type checker sets up this equation. fa is equal to option int 32. Unification solves this structurally. F is option, A is in 32. Okay, but like, isn't this literally not working for me right now, right? We are trying to do unification, the constraint that foo integer and f integer is the same, so doesn't it mean that f is equal to foo, right? Let's try making this specific example. Literally the same code, but in Idris, right? Can I say foo x foo? Can I use underscores here in Idris too? I have a foo. We don't even need to give it a definition, right? So just say foo someone. Foo just one. Okay, yeah, there we go. Let's try this again. Type foo just one. So what's this error then, huh? The problem is not higher candidate inference, the problem is numeric defaulting. What Idris actually sees, you typed foo just one, Idris passes that as just one, maybe integer. Because numeric literal default to integer, just without annotation becomes maybe integer. So the constraint generated is fa is maybe integer, but your function requires fa this. So now Idris is trying to solve question f, question a. What? Well, also needing the result type to be this. That would imply this, but maybe integer is not maybe int 64. What? I think ChatGPT is too stupid for the dependent types in it and Idris. This makes no sense here. Does Idris just not do this kind of inference? Like, why do the monads work then, though, right? Because is it like having some special stuff in the do notation? Can I say that like? Can I say like do block cannot be empty? Do can do something like abstract. I need some operation that works like generically. You're basically re-implementing Idris Agda style implicit unification. Respect. Hold on, Idris Agda style implicit unification. I mean, yeah. I mean, are we sure that it's not flying? the failure is literal defaulting. I don't know. Let's okay, I mean sure, let's sure, let's just say f foo just hello, because there is no integer anymore, right? No integers. So what's wrong? Do just on its own is monadic. So you expect f is maybe a string, result is maybe in 64. Totally reasonable, except for one fatal detail. The real constraint Idris is solving, when Idris is foo just hello, it must check both the argument type and the result type. But you are in the REPL typing foo just hello with no expected result type. So Idris introduces metas. This actually might make sense. Hold on, this might make sense here. Yeah, because I did hear that in the REPL it's something different. So I want foo just hello, right? Can I say here that x is foo just hello and x is in 64. If I do this explicitly, maybe it's not valid argument in foo postpone. Alright, maybe I just don't know enough Idris to understand how to do this anyway. Let's ignore this issue. How does this work in Haskell? Okay, how does this work in Haskell? Let's do Haskell. Let's do Haskell. I mean, this is the example with the monad, right? That's what I'm trying to do. Like, do x is opt, y is sum 2, sum x plus y, right? Or, I guess the simpler thing would be just... the simpler thing would be just f is do, x is sum 1, and then we return. Do we have to do the return here, or like just on its own is monadic, so we just do just x plus 1, right? Like this. Does that work? F is just 2, right? So here's the question. So this is supposed to this is just the syntax sugar, right? The do notation is just syntax sugar. What is the syntax sugar for? The syntax sugar for just 1 into lambda x into just x plus 1, right? They use the fat arrows here. Okay, sure. I was trying to guess the syntax of Idris. So G is just 2. This is the same thing, right? This is the same thing. This operator here, this operator here, is just the this is the flat map from the monad, right? Already. So the question is, what is the type of that, I guess, right? What's the type of this? Type of that, right? So this is monad M, MA into AMB into MB. So how does it figure out that M is option in this case? That's my question, right? Is a maybe. Because we're basically calling a function, right? Let's just define this ourselves, right? Flat map is the name of this thing, right? So this is basically this test type. I mean, this is not exactly implicit argument, so it is a little bit different, right? So is it like a different syntax which works completely differently? Can I just say M, MA into AMB into MB? Mismatch between A into B and type. Does this need to be in parentheses? Some reason. Oh, it's a fat arrow there, right? We don't do a dot. Dot is from Haskell, but in wait, hold on. Can I just say MA? This is like going to be just implicitly defined, right? No, this is undefined name. I need to define it. Ah, M. What's the problem now? Oh, I need to like say that M is yes, MS type into type. Like, is this different? So type of flat map is this, which is different from this type, right? So how are these types different? This is a dependent function with implicit argument, and this is the polymorphic function, and this is different in Idris, am I right? What's the type of monad? Type into type. Yep. Makes sense. So this over here implicitly defines this argument, right? Maybe I say for all M. Oh, wait, this looks like this is the syntax, and this can be like ignored. So can I remove the monad M and stuff? I can. Okay, nice. Type of flat map. Okay. And as you can see, for all M is basically the same as this then, right? That's what it says now, that we have 0 M. I don't know what 0 means here, but basically, yeah, okay. And let's call this flat map 2, right? So what's the difference between these two types? What's the difference? There is no difference, right? Okay, except for this 0. Whatever that means. Hold on. What does that 0 mean? It means this argument is erased at runtime. 0 is quantity, multiplicity. In address 2, every binder had one. You just usually don't see them. 0 is erased. 1 is linear, must be used exactly once. Okay. Sure. So for all introduces the one that is not used at all. Okay. At runtime. That's fine. But anyway, so if I try to use flat map using just 1, 2, 3, it says cannot solve constraints. Wait, so is this inference only happening inside of the do notation? Wait, no, there's no way. Hold on a second. If we use this, just 1, 2, 3. There you go. So this works. So there is a distinction between these things after all. Because, so it's solving constraints between maybe integer and MA. But in this case, it solves this constraint because in addition to this constraint, it also knows that M must implement a monad. But like, why is this required? Like, we already know that this is a maybe and this is an integer. So this is a maybe, this is an integer. Why is specifying that we need a monad here is required for this constraint to be solved? Why, if I define flat map like this, just like this, but without needing monad instance, then inference fails. Because this cheats. You only gave one argument. After partial application, Indra is trying to parse this. But how is it cheating? So why does this work? Because type classes change the game. Okay. They actually do. Recall the real type, yes. So am as a constraint. And constraints are active inference drivers. When it receives this, it does this. Just one, maybe integer. Therefore, m is maybe. So why is m is not maybe over there? There is no expected types to force m to stay maybe. What? It does not commit to higher counted metas from a single argument in beta expression. Proof or liar? It does not globally infer HKTs, guess constructors for type, backtrack on raised implicits. Committing early to m is maybe would be unsound in general once effects, interfaces, and raised args are involved. Link. Contrastive experiments that elaborator cannot escape. Same shape, first order type, no HKTs. ID1. A type is this. Because the meta is first order. Address commits immediately. Higher kinds by forced by result type. This works. Flat map. Just one is this. Why? Because now the expected type generates this. Okay. Forced by constraint. Apply higher kind function type FA. Apply HX, X is X. Now try apply HX just one. Cannot solve constraint between maybe integer and FA. No extra args, no constraints, no expected type. This is the minimal case. One argument, higher counted implicit, bare expression. And Idris refuses to commit. Why? This is structural, not accidental. You ran straight into the boundary between Hindley-Milner intuition and dependently typed bidirectional elaboration reality. Unification and implicit arguments in Idris. These are some unsorted notes on aspects of the implementation. Sketchy. Unification is probably the most important part of the elaboration process and infers values for implicit arguments. That is, it finds values for the things which are referred to by meta in term. So meta is the implicit arguments. That's what they call them. The unify interface I mean, sure, whatever. Elaboration overview. Bound implicit. The raw emp type has that. Unbound implicits. Any name beginning with a lowercase letter is considered an unbound implicit. Okay, so this is like implicitly creating implicits. Okay, makes sense. A question mark in a type means infer this part of the type. This is distinct from underscore in types, which means I don't care what this is. The distinction is in what happens when inference fails. If inference fails for underscore, we implicitly bind a new name, just like pattern matching on the left-hand side. It means match anything. If inference fails for question mark, we'll leave it as a whole and try to fill it later. As a result, we could say vect question mark. No, it's just like a standalone question mark though, not like F question mark. Linear types. Wait, it just has linear types too. Local definitions. This page explains the implicit argument section, how Idris turns unbound names into metas, and how unification solves them only when enough information is available. Implicit arguments. Over here, when we encounter implicit argument underscore in the raw syntax or added, when we elaborate an application and see that there is an implicit needed, we make a new whole, which is a fresh name applied to the current environment, and return that as elaborated term. This happens in this place with the function metavar. If there is enough information elsewhere, we'll find the definition of the whole by unification. Yes, that's what we try to do. We never substitute wholes in a term during elaboration. And rely on normalization if we need to look inside it. We never substitute wholes in a term during elaboration. If there are wholes remaining after elaboration of a definition, report an error. It's okay for a whole in a type as long as it resolves by the time the definition is done. That's where cost is different. See this. Make implicit to see where we add holes for the implicit arguments application. Elab app does quite a lot of tricky stuff. In an attempt to help with resolving ambiguous names and record updates, it will sometimes delay elaboration of an argument so that it can get more information about the type first. Solve constraints revisits all of the current unsolved holes and constrained definitions and tries again to unify any constraints which they require. It also tries to resolve everything defined by a proof search. The current state of unification constraints records which meta variables are blocking them. This improves performance since we'll only retry a constraint if one of the blocking meta variables has been resolved. This doesn't give me the information that I want. Parameterizing over higher kind. Oh, hold on. Stack Overflow. Stack Overflow. Ah, light. My eyes. I'm using a demo example for jQuery isotope. Wait, what? Wait, what? Where's Idris? Once you sign in, I'm not registered here. Oh, it does become. That's weird. Tutorial implicit arguments. We have already seen implicit arguments, which allows one to be omitted. Auto implicit arguments. Yeah. Default implicit arguments. Literate programming. Cumulativity. Hold on a second, what is this? Not yet in Idris 2. Since values can appear in types and vice versa, it is natural that types themselves have types. Oh, yeah. Then there's like multiple universes. We don't do that yet. Without an expected type or constraint, it won't commit a higher kinded meta from a single argument. There's no... And this Stack Overflow, I don't know, like over here, ChatGPT just talking nonsense. Completely. Yeah, okay, I just don't understand how the higher content inference should work. I didn't do anything useful today. Let's do something useful, huh? I guess I'm not going to do that today, because I don't understand how the algorithm, like how should this be inferred at all right now. You didn't try Haskell? Well, I mean, I would expect it to work the same in Haskell. I mean, okay, fine, let's do Haskell. Haskell Playground. It's just like in Haskell, what do I want? I want to see, I mean, GHCI is what we want, right? GHCI. Can I say like F is, so basically we want for all M, which is star into star. That's how we do it, right? MA into MA. Variable not in scope. How do I declare a new thing in the GHCI? Okay, Nigel, you know how to do this, right? I want to not give it the implementation, but just like give it the type first. F is equal error to do. Okay. Star is yeah. You are supposed to write type instead of stars these days, right? So the question is, what is the type? Can I specify the type of like F just 1, right? Num A, maybe A. Yes, so this works. This actually works in Haskell. Why does it not work in Idris? So like, isn't this the same thing? This is the minimal example. Let's do like the same minimal example in Idris, right? We just say that f is, so you have like m, which is type into type, and then you have like m a, so you have like another a, which is type. Do you know sometimes your terminal doesn't update for stream? You read num a, maybe a, but didn't actually see it on stream. Wait, really? Type of f, just 1. Yeah, see, this doesn't work. Like, this is literally the same definition as we just were doing in Haskell. Oh, I mean, I guess we just say is no type, and you cannot use type, so like you must use a star, but then star gives you a warning. Use type, oh, data kind, like I'm going to open the module first, right? Somehow. Yeah, type of f, just 1, right? Just hello, maybe string. Yeah, so okay. I'm tired. I need to go. I think let's just do something useful before that. I will think about this more. Maybe I will like figure it out. Maybe I will figure it out. Let's instead do something useful. How about the result type that you wanted? You didn't add the pull request yourself, so let's do that for you. Okay. Oh, by the way, I wanted to do something else also. Not sure if I want to do that now, though. Sure. Let's start with the results. Although, like, what do we use the results for? We don't use it for anything yet. What would you use the result for? Because, like, technically, I want to be using the effects instead of returning results from functions for error handling, I think. I mean, this over here, but like, yeah, once again, I think this should not return a result if this failed to execute a command, for example, in stdsys. We can define the type, that's not the problem. Let's do something else, something better. How about this? So far, when I was doing the advent of code, we were writing doing this. Where's my LSP? Oh, LSP is disabled for this because in the workspace I don't have day one, I guess. No. That's the reason. Okay, so we just have this thing where we do this string lines and all of that. Like all of the iteration doesn't use the actual for syntax, you know. How about we do like iterators or something similar? I have an idea of like the simple approach for now, so that we at least like write code as if it is done properly. Right now in the syntax rules, we have for. So we have a dedicated syntax for this in a range, but a range should just be an iterator, I guess. And let's just do instead a syntax just for 7.5 rep ever. We just do for pattern in so this is going to be, I guess, iterable or something. Do body like that. So we don't do in start end like this, right? We do for pattern in iterable. Loop var. We don't do loop var. We instead, so like here's what I think we should do. Let's create the let's say that iter is a module. How about that? I want the iterator. Iterable, I think, is what I want. We'll see. So this is going to be type T, which is like the item or whatever. Hi, have you tried not hating programming? Hello. I tried too much, which is the reason why I'm hating it, I guess. An iterable is something like this, you know. Iter is just a function basically, which takes the consumer, which consumes the item, like that. Yeah, how about this? Does this make sense? it's like the producer of the items, and we supply it with the consumer, basically, for now. Yeah. So over here, this iterable is boom, 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 boom. Is it like a trait? That's like a trait, probably, right? So do I say iterable? If this is a trait, then it should take self here then. Well, hold on. So if we do the iterator trait like in Rust, then we must have the associated types. Associated types is something that we cannot do that yet. That requires dependent pairs, I think, and like dependent tuples. Yeah, we don't do yet. But yeah, we should instead say, like, if this is like self, then this should be like item is type, and then this is you know, self.item into this, right? Then like self or whatever. I cannot do that yet, so let's do that. So it's not a trait, basically, but we expect the type here, I think. So can I just say that iterable is std iterable underscore, just so that we assert that it's an iterable, and then we just do dot iter, and then we have a function which says pattern, and then we return body just like this. That's all. Right? That's literally the entire thing. We just want to have like the breaks. We just want the breaks. So we will do something similar to this. So we're going to have continue and breaks from inside. So instead of loop, here we're going to do that. Pattern iterable windable body body. So that's what the for loop should be sugared into. So for example, we have a string lines, right? What I want to be able to write, is I want to be able to just write for line in string lines string lines of something, right? std fs read file, I don't know. Yes, so right now lines is a function that returns a unit, so we have this thing. So let's change this. What is the string lines? I guess this string lines should take the string and just return the iterable string. Get carried. Yeah, like in this case it is carried basically. Yeah, I guess. In this case it basically becomes a carried function, yeah. That's all. So we return the function f into like all of that, right? That's the function. So we say iterate is that. Why did it not do iter dot? Oh, that's a little bit weird. Oh, because it's a const, maybe. Interesting, anyway. No std in this scope. Oh, because I didn't need it with std. Okay. So this is supposed to work. Can I just say print line here? This just like makes the code look nicer, I guess, with a regular for loop for now. And then we can also like kind of like map the iterators in this, right? We can do like std iterate like map. We can do that. Technically, map s plus s const map is a iterator which is iterable a, so there's like a, b, f. Why not also add carry to stdlib? It depends on the number of the arguments. Over here, this also doesn't work, right? We need to, like, if I do map, because we don't have methods right now, unless this is carried, I cannot do the piping here. So I cannot do the map like that, really, right now. Unless I make map the carried function. I just really want to do this carried. We need to implement methods, I think. But sure, let's say f is a into b, and this returns iterator, which is iterable. A should return iterable b, where iterate is function consume iterable a is not a steady iter. Unless you implement uniform function call syntax. Yeah, that will require changing the syntax though. Let's keep this current for now, but like I should not add more current functions. Just for testing is what I want this. My LSP is having a bad time right now. I wrote this up before, but Lean has pipe operation without carrying. It sends left-hand side of pipe to first argument of right-hand side. Yeah, I know. Like, there's not the only language that does that. But the problem is then that function arguments are a little bit special. They are not just like you don't have like functions which are always having a single value as the argument, where you construct a tuple and pass to it if you want multiple arguments. It means that function algorithms are actually special. Well, I mean, most of the programming language have function arguments as a special thing. So like when we say it sends it to the first argument. But like you know, you have a function f which takes a and b and returns and does something with them, right? So what I can do right now is I can say that I have a tuple which is like 1 and 2, and then I call for like tuple, I pipe it into the function, right? This is a function taking 2 arguments, right? So should this be the first argument? So should this tuple be a, or should this tuple be both a and b? Or does this now depend on the type and not only on the syntax? Because that would be weird, I think, if it depended on the type, right? So if we want that behavior, then it must be special. Function arguments. Wait, this one over here is unexpected? Wait, what? Why? Oh, this over here, this one is unexpected, I see. Yeah, that makes sense. That makes sense, I guess, because this is not right associative. Because I don't want to support carrying, which means that I probably want to put this in parentheses. Okay, there we go. So now we just see every line twice. And I can pipe this thing into the map. Sure. What are the other things that we do? We have like lines, split. Split is another one, right? So split, we have a string, character. So this should return a triple string. We do that. Split once just returns 2 of them. 3 matches contains. Also lines. Isn't lines just splitting over the separator, which is a /n? Why don't we just say that lines is just s into split s/n? What happens? What if you extended pipe syntax to left-hand side, right-hand side, right-hand side arg, and right-hand side arg is not allowed to be anything but a tuple? Like syntactically, you mean? But what if there is a single argument that is left? Like you have the function with 2 arguments, right? You have a into fb, right? By the way, so you say in Gleam it passes as the first argument. In OCaml, if you do this, it would be the last argument, not the first one. So OCaml and Gleam have inverse semantics in the pipe. It only depends on left-hand side f being a function with arity more than or equal than 2. Left-hand side dot RHS arg. Well, hold on. This actually could work exactly as you say, but but it means that in order to do this, then you would have like to make this a tuple. You would have to like do a comma like this, which is like ugly, right? Also, my value, my func empty is valid call. Yeah. I think we can do this kind of like we need to like change the syntax. We need to, first of all, I think we will like fx, we will require parentheses here, I'm pretty sure. In order to call the function, let's require parentheses. Then when you have a function argument and you pipe it into function, you must still use parentheses, right? Then yes, like you have to use them. So this means that this is a function call here, right? Entire aesthetically broken. Yeah. Yeah, so we always see the parentheses here, and because of that, we can like syntactically inject the thing. Add a comma there, right? So then we will just implement syntax arg into f, other args, right? So that is literally just going to be implemented as function, as like function, argument, and other args, like literally. Well, I mean, yeah. But this means that like this well, I mean, this means that other args are not empty, so we will have to have two different implementations, this one and this one, which is empty. If it's empty, then we just literally do that. Because we're calling a function with no arguments. That's now different than calling a function with a single argument, which is a unit, you know? But right now, this means calling a function with unit as an argument. Wait, but what? But now we want to have functions which actually have no arguments, and how do we do that? Okay, again, I don't know. Why do you pass arg as first? That's how they do it in Glim. I don't know. Does it make sense to be more as last? If OCaml and F# do it as last. But that's because those are carried languages. Okay, over here, iterate over a string. This takes the function as the thing, yeah, but we can still implement that as the thing returning the iterator character. If yourself, this is actually first argument, then first makes sense. Scala uses fluent approach. And then list dot take 10 dot skip 2 like this. Yeah, but this is not piping, this is methods. I think that maybe we just don't need the pipes at all. We just need methods. It's different. It means that you don't have take as freestanding functions. Piping is not methods, no. Methods are namespaced based on the type. And piping is just piping the argument into a function, which does not belong to a type. How do we implement iter I using this? I mean, we don't need iter I because we can now do iterate enumerate if we do that.
Hello Dev 9-inch nails ya.
Hello Dev 9-inch nails. Let's keep this though here still. Iterate is f. Iterate as dot iter. There is a little bit of too many iters next to each other here. I mean, you know what, actually, let's just say iterate and enumerate. Why do we like shorten the iterate into iter, but we don't shorten the enumerate into enum? That's a question that's bothering me now. Okay, fine, we'll do one more current function. One more is not that bad, right? Well, I mean, this is not even courage, so like, it's whatever. Will you just formalize functions to always be tuple type? I don't know. Do you think we have to? Did you just create that? My formatter is deleting the code again, by the way, for some reason. Oh, there we go. Now this works. Maybe? It doesn't? No, why not? Sometimes Rust FMT removes comments. I don't remember that. Oh, it's because I'm using the iterate or iter_i in some places, right? Iter uses that. Yeah, iter_i is used here. Okay, so here's what we do. Here's what we do. Over here, this is unwindable block. But we okay, hold on. Instead we do with return here, right? Because we have return. Let's not do that. This just return I. Right, let's simplify our code a little bit here. This is not iter_i. This is just for I and C at I in iter_i as. Do I need parentheses here? Yeah, I do. So we do that, and then we just do that. And I don't need this else either. I'll probably just do this. Boop. If I can. Cast formatter. It's not correct code. No, my cast language server does not want to do the formatting for me. Reload. Oh, there we go. Why did I have to reload the window? That's weird. Last index off. Bam, bam. That iterates forward. Okay. Don't forget about me sized tools Rust FMT, and it removes the code. Nice. So I'm not the only one who, well, I mean, Rust removes the comments. I removed the code. So but it's probably because the LSP did not like catch the latest updates or something. Do you gonna implement tail call optimization? Happy New Year, guys. Happy New Year, Robert Pattinson. There are so many optimizations that I should do before tail call, though. I have a feeling something is happening right now. My cast is using 3 gigs of RAM and using the full core. We have 3 cast executables. Each one, and then combined it's like 6 gigabytes. All right. Everything is fine, right? I try over here for INC in try S. If C is equal to separator, then perform split. Remove that. Unwindable block to do panic. Oh wait, hold on. We actually have panic, right? Panic. Separate. Split. One separator. Not found. We can't do that. Unwindable. We don't do unwindable. We do instead return. Because we have with return here. Do you think annotating the thing with return is annoying? Okay, there we go. A restart, please. I think that works. Do we have iteration anywhere else? We do have iteration in other places, like in the trips. Iterate mutably, sure. So here also a little bit annoying currently. Oh, that's the other one. No, no, hold on. What? This... unit doesn't have fields. Why not? Say without formatting. Unit doesn't have fields. Is this unit though? Iterate data left. Oh wait, hold on, by the way. Oh, it's because like, yeah, the inference is broken because I'm using this function over here and I'm keeping this type. Which actually returns unit. Yeah, so instead over here, this is toString, right? We instead just do for x in iter v. That's what we do. Empty returns unit. Oh, this one, yeah, maybe. Wait, no. It doesn't matter. Like, this is the function that should return unit. This is a consumer. This should be a reference t into unit. Yeah. If you meant like this branch, it should return unit because this should be function. Wait, like look at this. This is inferred incorrectly. If I comment this, right? What is this f? We don't know what f is, which is weird because that's part of the iterable interface, right? It should be item into unit into that. Oh wait, hold on. Oh. Maybe just use somewhere else. We have yeah, because we are using the iteration over here, right? To iterate over a list. Yeah. Trip iter much this inner. Trip t iter mut. This is different. This should return iterator. Mut. That should be very similar to this. I don't have this as a syntax yet, do I? Wait, hold on, I actually do? Wait, hold on, I do that. Yeah, I do this, capture my reference. This to do is actually done now, right? Unexpected mut. I think I need to maybe ref mut like this. Unit doesn't have fields. no. Oh no. Now we have a very... data string... iterate... T cannot escape scope. Hold on. No! My stuff is all broken now. I started touching code. And everything broke. And my error messages are horrible. No! Must delete. And start from scratch. Right, Nigel? It's a rewrite time. What's the problem? Let's just, you know what? What we need to do is I need to comment out everything except for, like, we use trip. Trip. There we go. If we just have trip, we still have an issue, of course. Of course. Oh, it's a semicolon. I found it. That was a semicolon. And over here was also a semicolon. I feel like this should not be like correct syntax, right? So basically, we have the syntax like this, you know, dot field is value and then semicolon. Then this is right now allowed, but it should not be allowed. Somehow. Okay, seems like standard library is working. Anything else I wanted? Not really. Oh, now that we have a for in, a generic one, right? What we want is we want to create a new thing for like the range. In iter as well. What do you mean? In iter as well. Old message? Okay, never mind. So one thing that I would like is to have like the reversible iterators though, right? What we can do is that this syntax just does this without type asserting. Can I just do iterable dot iterate like this? You know? And then in this case we could have a reversible iterators. Const reversible iterable reversible. But this should, yeah, but this should be traits and stuff. Yeah. So we'll have like iterate. But in order to reverse an iterator, if we have it as a function, it basically means that we need the reverse iterator to also be the other one, right? The other iterator, basically, like this. That's what we want. or rather, reverse should return the thing itself. Maybe. Before doing this though, like I said, I think we want in the syntax rules to now be able to do a range. So this should be like above 4. Reversible iterator does not make sense in iter APIs that aren't like Rust. Well, I mean, I'm going to... The current plan is to do it like Rust, with a trait. So instead of just returning the type, we will return concrete types and then implement the traits for them, right? Did I comment the non-empty trip? Not sure. No, I did not. And this should be iter mut. And this should be mutable. Ref, oh wait, hold on, I don't have the way to do ref mut data right now. Do I? Like, I don't have a way to do that, right? Not mutable. This is supposed to be a reference, so like, shouldn't this be technically here? That. This should also be by reference, by the way. Let's start with this one, which is the not mutable. This should be node reference data. So since this is a reference now, we need to dereference it first. That's like the correct way. What about pipe operators now? What now? What changed? Reference does not have field. Yeah, this is the same issue. But the problem is that this is not mutable because we don't have the ref mut, I think, right now. Will you do it as mut self into option item? No, I don't think so. I don't think so. Oh, I mean that's the iterator. That's not why I'm not calling it iterator. I'm calling it iterable, which maybe should be like something like some other name. That's why I didn't call it iterator, because I don't have the next method, but I'm just iterate over the entire thing instead. You don't like the ligature for pipe operator, actually? Option is none. Oh, nice. Invalid argument. Option is none. Hold on. Cast parse echo ref mode x. There you go. That's where option becomes none, right? Wait, what? Hold on, it cannot parse it. Oh wait, it cannot lex it. Wait, what? That makes no sense. What? The lexer doesn't work on this? That makes no sense. Which option is none? Parse line in the rules. Oh, it's parsing the rules. Okay, hold on. It's because this over here. That makes sense. I was trying to implement the range. The range. I don't know what priority should be, but it basically is start dot end. That's what I want. Implement syntax start to end as iterate is okay, we just say something like flat not index is start while I is less than end. Do I plus equal 1. No, we don't do this because we need to iterate, right? This is like consume. I do this double underscore because I don't have the hygiene yet as another thing. Consume I plus equal 1 while I is less than end. Dollar. Okay, so we want to calculate the end only once. Is this PHP? Do they do double underscores there? Or you mean like the dollar? The dollar is the unquoting. So do I parse? This is unexpected. Ref mut. Do I want to implement the ref mut right now though? That's the question. Probably not. Let's go to trip. Let's instead do to do ref mut. So we just say mut data like this, and then I just say let data is mut data for now. But this technically like copies this thing out, although it doesn't really matter for me currently. Cast is PHP 9. Dollar is used in a lot of languages to, like in string interpolation, like Bash uses dollars. In this case, we interpolate the ASTs though, not strings. Okay. Okay, well, I mean, I guess what we can do is we can test rewriting the day one code, project under code, source, day one. We're just going to say here, right, read inputs over here. We do string lines, right? We instead just do now for line in string lines input. Like that. If line is empty, then continue. Just flatten this thing. I really like doing the memes, right? PHP 9 cast. Tough decision. And one of these memes is actually going to be good. I can see. You need to practice more though. Over here we do list iterate. So we just do for instruction in list iterate input, right? Like this. Like it removes 2 levels of nestedness, basically, this thing, which is nice, right? Okay, it looks like this code is still working. If it works correctly, I don't know, because because everything is really slow right now. But we did do that. So I can also say that for I in like 1 to 5 std dbg print I, like that. No, this doesn't work. Okay, what's the problem? Oh, that's right. No, this makes sense actually. The reason it doesn't work because I don't wait, what? No, hold on. Because I don't infer the type? Wait, but why does it need to be inferred? Something is not inferred. Line column 10. Which one is 10 here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we don't know what the number is here. So do I need to say int 32 here? And then this must be in parentheses, it seems. std print I. And then this works? Okay. Yeah. Why is my, like, auto-completion? We just use the arrow wrap. Just, like, limits the length of the line that is auto-completed. Weird. Then there's the reversible, right? So the thing is that this can be reversible. Can I create reversible thing though? I feel like this should be instead do std reversible instead of reversible. std ops. Like in Rust, the range lives in the ops. Why does in Rust the range live in the ops? I don't know. Should I put it in the ops too? These are just like the operators. It's nothing to do with the range. I can make the range module instead. No, there is a steady range. Oh, but this is the replace. Wait, hold on. Experimental replacement range types. What is this even? The types within this module are meant to replace the existing range. Oh, okay. And then they're putting it here. Interesting. The new range API. Range from, range inclusive. Nah, let's have the range over here. So range, and we're just going to have the function, you know. What do I call it? Just range. Start. Team. Should this be generic? Start, team, end, team. Oh no.